At this point, I'd like to introduce Matt. Matt Lauer is a high school teacher and college physics professor with a strong interest in promoting science education and critical thinking among his students and the population in general since 1998. He is a self-described skeptic, someone who believes in Carl Sagan's adage that extraordinary claims require extraordinary evidence. Thank you. In addition to his normal teaching studies or duties, he's currently working on his bachelor's in philosophy with the hopes of eventually researching the philosophical borderlands between science, non-science, pseudoscience, and religion. He muses on these and other topics in his blog, The Skeptical Teaching. Among other things, Matt also contributes and sits on the JREF Educational Foundation's Educational Advisory Board, that is the James Randi Educational Foundation's Advisory Board. Please help me welcome Matt.
Thank you very much. It's nice to be here. It's nice to see some familiar faces. And some not so familiar faces. And I hope we can have some fun this evening. Those of you who've seen me speak before may recognize some of the things I'm going to talk about. But this is a completely new talk in the sense that it deals with subject matter that traditionally haven't spent a huge amount of time on for yourselves. As a girl said in the direction, I'm a high school and college physics professor. I've taught astronomy before as well. And this is meant to be sort of a public talk, kind of a nice mix of science and philosophy, because, as the judge said, that's kind of the stuff I'm into. And if you have any questions as we go along here, feel free to raise your hand if it's a really urgent question. But we're probably going to have plenty of opportunity for hopefully a vigorous question and answer session at the end, and so on. So let's go on and get started. I titled the talk "Life, the Universe, and Everything," sort of, because, well, as you see, we're going to kind of get into all of those questions here. And Shane's plug for my blog there. And this is my favorite cartoon ever. These two scientists or mathematicians or whatever, they're working on some complex problem. One's critiquing the other because there's this kind of interesting step in the middle of it. The miracle occurs. Criticism says, but it needs to be a little bit more explicit right here in step 2, because it's been my experience that once you start to invoke miracles as an explanation, then inquiry kind of shuts down, and it's going to be antithetical to the whole scientific and philosophical matter.
Matt, would you mind speaking up a little bit?
Oh, sure.
Or holding the microphone up to you?
Okay.
Just so that the
Can I raise that a little bit?
You can remove it.
Just, there we go.
It's close to your mouth. No, you have to pick it up.
There. Ooh. Yeah, if it was too close, it was good. Okay, there we go. Sound better?
Yeah.
Yes.
Okay. All right. So, what I want to start with here is just a reference to some features of our observable universe. And you're going to notice I'm very careful with my language here. Pay attention to the fact that I'm saying observable universe. Right? That's a very important thing to know. Look up at the night sky from Earth, and you see wonderful scenes such as this on a very clear night under ideal viewing conditions. It's the Orion Nebula, arm of the Milky Way galaxy, the star Sirius, and so on. And every dot that you see, every bright point in this picture is a star. And then you, with enhanced technology, such as the Hubble Space Telescope, you can see views such as this. This is called the Hubble Deep Field View. By contrast, where every point of light here is a star, every point of light here is an entire galaxy of stars. And just to freak you out with some numbers, what we're talking about here is in our own galaxy, we have approximately 100 billion stars. So it would be 1 followed by 11 zeros. And in our observable universe, so we're observable again, we have on the order of around 100 billion galaxies, right? So if you do the math, that comes out to, I don't know if there's an actual name for this number, but it's 10 raised to the 22nd power. That's a 1 followed by, or 10 rather, followed by 22 zeros. And it's quite a large number. It's so large, in fact, that it's almost impossible to wrap your head around, because we're not used to dealing with numbers like that. But it's a lot. But as you're going to see, maybe it's not as much as we think. We'll get into that in some more detail. One other thing I want to point out about these pictures is it's very important to understand that light travels at a finite speed. So because light travels at a finite speed, when you are looking at starscapes such as this, or galaxyscapes such as the deep field view, you're quite literally looking backwards into the past, because it took light a certain amount of time to travel from that originating point to you. For example, in the case of the star of Sirius right here, I believe that's roughly, from the column correctly, roughly 8 light years away. So what that means is when you look at the star of Sirius, you're not seeing it as it appears now, you're seeing it as it appeared 8 years ago. And some of these galaxies that are in the deep field view and whatnot, they can be as far away as billions of light years. So you're literally looking billions of years into the past. Okay. So in a very real sense, astronomy is kind of like you're in a time machine. It's pretty interesting. Now, bear all that in mind as we start to look at the next picture here. It ends up, if you do a broad survey of galaxies out in our observable universe, and I call it our observable universe because this is the part of the universe, our universe, that we can see because the light has taken a certain amount of time to get to us. Conceivably, there's parts of our universe beyond which we have not seen yet because the light from those sections of our universe hasn't gotten to us yet, so it's kind of waiting for that signal. But if you take a broad survey of our observable universe, and again here for scale, you can see that we're assuming that this is us, and these are units in billions of light years, right? So farther and further in the past, that you see very interesting structure. Now, a couple of things I want to point out here. First of all, you see these kind of slope-like structures here, and here, and here. Those are features that are just an artifact of basically something being in the way, right? So if you're looking out with a telescope and you're counting galaxies, every little blue dot here is a galaxy. So yes, wow. Don't worry, it's way crazier, just wait. So if you're counting galaxies out there, and there's something in the way, like a cloud of gas or dust, or say the center of our own galaxy, right? You can't see past that, so that's kind of causing it to be a blind spot in vision, so to speak, right? So these are like shadows in that sense. There's something in the way. This is kind of a blind spot that we can't really see what's in there because from our vantage point, there's something in the way. But despite that, you notice that there's some interesting features here. You notice that there are clumps of galaxies, such as these big dark blue splotches here. And these are humongous structures. They're hundreds of millions of light years across. But at the same time, you notice that there's these big gaps here, these big voids where they're almost completely empty of galaxies. So this structure in our universe sort of has this kind of strange web-like structure. And one way to visualize that is with a picture like this. Now, this is a computer simulation of our observable universe, and you can see the web-like structure that I'm talking about. You get these big clumps, and oh, by the way, just for scale here, if you could zoom in on this, you would see that this is composed of a bunch of little tiny dots, and each one of those little tiny dots represents So this is kind of like a three-dimensional picture of what you guys saw. In a more broadly computer simulated sense. And these big red clusters here, these are what are called, often called superclusters of galaxies. So they're really enormous structures. They're many, many hundreds of millions of light years across. And then you can see the kind of webbing that I was talking about, the filaments and the big gaps and the voids in between. And this structure, this observable universe stars, is approximately 90 billion light years across. Okay, so it would take a beam of light 90 billion years to go from one side of this cube to the other. Okay, so let's stop and think about that for a moment. That's pretty big. But again, remember, this is our observable universe. Right? This is the part of the universe that we can see. Presumably, there's no reason to think, as far as we know now, that there isn't stuff out here that we haven't seen yet, because the light from this stuff hasn't quite gotten to us yet. Because, as we know from our understanding of modern cosmology, the universe has a finite age. Right? It's approximately 14 billion years. So, if the universe is approximately 14 billion years old, then...
Billion.
Yeah, 14 billion. Right.
I'm sorry.
Billion, yes, a billion billion. Yeah, but if the universe is 14 billion years old, then light has only had that much time to propagate. Now, let me clarify something, because I just used two sets of numbers and some people are probably very confused by them. I said the universe is 14 billion years old, but I said this observable universe of ours is about 90 billion light years across, and those numbers don't seem to match up. Remember that I said that this is a computer simulation, right? The difference between these two pictures is this is what we've actually seen, okay? And what this is this is a computer extrapolation based off of this data and similar data. Because what this picture is showing us is if we could see our universe, a whole of it, right now, and not just this sliver, then we think it would look something like this. Okay? That's what we're getting. Okay? Question?
Well, I thought that effect, the fact that it's 90 billion light years, is primarily due to metric expansion of space, though.
Yeah, well, what you got is and it's something we'll get into in a little bit, the universe is in a state of expansion, right? So what happened is, say, billions of years ago, there was a section of our universe which was closer to us, and then in the intervening time, it expanded, it got further and further away as space-time expanded. And when that happened, again, we're always playing catch-up with the light, right? So this is kind of like what we think it would look like now if we took all of those calculations into account. You understand what I'm saying? Okay.
Now, since we're sort of defined as Earth's revolution about the sun, how can you look before the Earth? The Earth is what, 3.5 billion years, 4 billion years?
4.5 billion.
How can you? Before the Earth started spinning, there wasn't any time as we recognize it. So how there weren't any years before the.
Well, you can think of it as how did people mark time with their clocks?
Well,
when you talk about marking time in terms of the Earth year, it's just an arbitrary unit that we choose based upon our experience.
But the Earth years are the stuff that's built into our DNA and all of our. It's more than arbitrary. It's determined.
Well, we could measure it in terms of seconds. We can measure it in terms of
seconds and all that are derived from the basic paradigm of the terrestrial axis and its adventures around the sun with the moon and all that. That's the basic paradigm of time. Everything else is a fractal iteration of some other dimension.
That fits into
You can't. Time is geocentric. You can't talk about time.
Time is not quite what you think. That gets into a different discussion, but I'll hit on those points a little bit more later. Let's take a look at the next picture. Okay, now I could spend a lot of time talking about various lines of evidence that we have for the Big Bang and the expansion of the universe and so on, but that actually takes a considerable amount of time to do that. So, and that's not really the main thrust of this talk. Suffice to say, there are three really primary lines of evidence, but there's many other lines of evidence for giving us the conclusion that our universe spawned, if you will, out of a very hot, very dense event about 14 billion years in the past called the Big Bang. Okay. And one of them is Einstein's general theory of relativity that actually predicted this, and every test that we've done in general relativity and its description of what we call space and time mixed together has proven valid. Another one is the abundance and the proportions of various elements throughout the universe, okay, because the Big Bang cosmology predicts very accurately what those proportions should be, and they are matching up with our observations. Actually, I said three, there are 4 points I'm talking about. Well, another is what's called the Hubble expansion of the universe in terms of the Doppler shifting of distant galaxies. When we look at distant galaxies,
The what shifting?
the Doppler shifting, right? So an example of Doppler shifting is if you are traveling along the road here and you have to pull over for an emergency vehicle, for example, because its siren is wailing. You pull over to the side, you stop, and as the siren is approaching you, it's wailing at a higher pitch, right? And as it passes you, what happens to the pitch? The pitch drops, right? It goes, that's a crappy rendition, but you can do it. And it ends up that light waves do a similar kind of thing, except what they do is when the object emitting the light is approaching you, it tends to look bluer, and then when the object that's emitting light is moving away from you, it tends to look red. We call it blue shift and red shift of light. Now, it ends up with the Hubble expansion, or the Doppler shifting I was mentioning. Distant galaxies are moving away from us because the universe itself is expanding. It's kind of like these galaxies are raisins stuck in a dough of bread, like raisin bread, right? You heat up the raisin bread in an oven and it expands. The dough itself expands and it carries the raisins with it. And that's kind of what's happening with galaxies in our universe. Now, the thing is that therefore we look at these galaxies and gives it a redshift, and then we can infer from that that the universe is in a state of expansion. And if the universe is in a state of expansion, that means that today it's bigger than it was yesterday, and so on and so on. And then you can imagine reversing that flow of time and imagine that the universe was smaller in the past, and you can extrapolate back and calculate how much time it took for there wasn't a universe. That goes up to about 14 billion years, and it agrees with all the other lines of evidence that I discussed previously. The fourth and final line of evidence, which I really want to focus on for the purposes of this talk, is this, the cosmic microwave background. Because it stands to reason that if our universe came to existence 14 billion years ago in a very, very energetic event we call the Big Bang, then we should be able to look out to the sky and see the afterglow, so to speak, of that event. Okay? And it ends up that you do. You just don't see it in visible light, right? It's not like you walk out at night and you look out at the sky's on fire. Okay? Because due to the effect that I mentioned a few moments ago, the Doppler effect, right? As the universe expands, you get the things that are far away, the light red shifts. It ends up that leftover afterglow for the Big Bang is redshifted so much that it's redshifted all the way past red light into the microwave region, right? It's called microwave background. So you can detect this if you have a microwave background. If you have a microwave telescope or antenna or something, you can set up and you can actually listen and detect this stuff. And if you go over our atmosphere, because our atmosphere screens some of these microwaves out, a lot of them actually, if you go over our atmosphere with a spacecraft such as the latest one to map is called the Planck probe, you get a picture like this. This picture is basically a microwave photograph of our early universe. Yes?
Could you please repeat what you said? You said it was inferred that we'd be able to see it in another form and not microwave. You just read something?
No. The reason you see it in microwaves, I'm sorry, the reason you see it in microwaves is because of the redshift.
Oh, that's right. I was actually thinking about that word. Thank you.
It's because of the redshift, because the energy that was given off in the Big Bang is extraordinarily energetic, but because we're looking, you have to remember, right, you're looking very far in the past, the further and further you look away, right? So what you're actually seeing here is this is basically a snapshot of what our universe looked like, more or less, about 300,000 years after the Big Bang, right? So this is about 13.5 billion years ago, roughly. Okay? And so that means you're looking very, very, very far away to see it. And because you're looking very, very far away to see it, you're getting that Doppler shift. That's the redshift I mentioned. Right? So all that really high energy stuff gets redshifted way down into the microwave region. That's why you have to use microwave detectors to see it. So, and there's a lot of funny stories about that, but unfortunately I don't have time to go into all that. If you want to read the most hilarious story of how people can win a Nobel Prize, just Google Penzias and Wilson, people who discovered this microwave background radiation, and it's the most hilarious way of getting a Nobel Prize ever, accidentally. Anyway, the thing I want to point out about this background picture is that, okay, so this is like our entire universe, and you note the different colors, okay? What this denotes is that there are very slight density variations, okay? So the bluer regions, like these areas right here, right here, right here, these represent slightly cooler regions of our early primordial universe, which we think correspond to slightly less dense regions, right? Because the more tightly concentrated material is, the hotter it will be. And the redder regions here, 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 and so on, correspond to slightly hotter regions of the early universe, so slightly higher concentrations. Now, the cool thing about this is, if you stop and think about this, this actually makes perfect sense given what we are seeing in our universe now. Recall this picture, right? Actually, well, this picture, but this is the computer extrapolation, right? We have these clumps, humongous clumps of matter, right, with big gaps of voids in between. Our early snapshot of the universe, our earliest snapshot of the universe, the cosmic background radiation, has clumps of matter with big gaps and voids in between.
What's the data that was taken to
This?
simulate this?
Oh, no, this is not a simulation. This is an actual image of microwaves. This was taken, the Planck probe, just within the last 2 years. This is our most recent data.
What's the Planck probe?
The Planck probe is it's a space probe that was sent up by, I think it was a combination of NASA and the European Space Agency. I can't remember exactly, but it was sent up for the express purpose of mapping this background radiation in great detail. The first probe to actually do this mapping was called COBE, Cosmic Background Explorer. It was actually launched in the early 90s. But, and it gave a good map, but it wasn't as high resolution. That's right. So this is just a higher resolution map than that earlier data. So we can see more and more detail. Okay, any other questions before we move on?
So the probe is aiming forward or is aiming 360?
Whole sky. Looking at the whole sky. This is a picture of the entire sky. Of course, projected wrapped around. Yeah, it's wrapped around. Yeah. You can find pictures where they have it kind of like it's wrapped on a sphere, so you could kind of like a globe. So you can actually purchase those. It's really cool, and you can say, if you look at this direction, this is what the background radiation looks like. Okay. Now, an interesting question, and this actually ties into the idea of multiverses, which we will get into in a little bit. An interesting question is, okay, so where did this sort of variation in density come from, right? I mean, how is it that you have this big gaping voids like this that, these rather, I should say, how is it that you have these small, these regions of slightly less density that led, we think, to these big gaping voids? and then these regions are slightly higher density that we left to this big clumping of superclusters of galaxies. You know, where did all that come from? And that's a fair question. And it ends up that one of the ways in which hopefully these questions can be explored, there's sort of two ways of looking at this. There's one is the theoretical way, which I'll get to in a moment. And then you got people who are actually trying to look at conducting experiments in the laboratory with this, right? We have here, anybody know what this is actually? Yeah, this is one of the detectors in the Large Hadron Collider at CERN in Europe. And just to give you an idea of scale here, this is a person. Okay.
Is that one in Switzerland?
Yes. And this is a very, very large machine. And one of the things that some people hope to do is they hope to actually recreate the early conditions of the Big Bang itself, because we have a pretty good idea of the amount of energies and densities involved in the conditions of the early primordial universe right at the Big Bang. And some people think that we can actually recreate those conditions on a very, very, very tiny scale, of course, in a repeatable manner in the Large Hadron Collider. So we actually have a way of directly testing some of these ideas. I don't know how far off those tests are, but it's interesting that we could be seeing that in the next 2 years or decade or so. But on the more theoretical side, one of the explorations goes into details. And so what we see here is we see the cosmic background radiation map that I showed you a few minutes ago. Okay, and then this is sort of a comparison. This is kind of like a little slice of that earlier computer simulation of the whole universe, okay, or rather, our whole observable universe. Okay, let's keep that in mind. And so eventually the idea is, okay, well, you know, these differences in density led to these huge variations, those voids, the filaments, and the clumping matter that we see in the universe today. But where did that come from? Well, one of the prevailing theories right now, which hopefully tests on Large Hadron Collider will be able to verify or invalidate depending on what happens. One of the prevailing theories now is that it has to do with the nature of space-time on a quantum level. Now, let me unpack that statement. Because I just threw out $1 million phrase, and it sounds good, but can I repeat? Let's see if I can get it exactly right. Has to do with the structure of space-time on the quantum level. I think that's what it's anyway, the idea is this is connected with an idea that's sometimes more properly known as quantum foam, or the uncertainty of space-time at very, very small scales. Let me give you an analogy to make sense out of all this. You can kind of imagine the structure of space and time in the way that Einstein envisioned it, his general theory of relativity, as kind of like a stretched rubber sheet. Right? If you have an empty region of space-time, it's completely empty. There's no stars, there's no planets, there's no galaxies. It's just completely empty. You can imagine you have a stretched flat rubber sheet. That's a representation of empty space-time. Now, if you take a massive object like a planet or a star or a galaxy and you place it in that region of space-time, it does what we call warping, or I like to say puckering the space-time. Right? You kind of get this pucker, this dip in space-time. And if objects travel nearby, then what you get is they deviate their paths. Now, Newton would call that gravity. Okay, so you can imagine that if you have a pucker in space-time and another object like a spaceship or something is traveling along, it enters that little pucker in space-time and it kind of deviates its path. This is the way we look at gravity in terms of Einstein's theory. This is our most modern theory of gravity. Okay, so you have that idea here that there's stretched space-time. Okay, so imagine that stretched rubber sheet is actually like the surface of the ocean. Okay? And you're way above it. Okay, you're way above it, and you're looking at this surface of the ocean. And if you're very, very far above the ocean, and you look at this surface, what does it look like? It looks nice and flat. It looks very calm. Okay? Now let's suppose you start to change your size scale. In other words, you shrink down. Okay, so you start to zoom in. And as you come down and come down and come down, you start to approach the surface of this space-time fabric, so to speak. As you get closer, you start to see a few waves and ripples here and there. Okay? And then as you get closer and closer, as you shrink down even smaller and smaller, what you see is little froth, and foam, and bubbles and stuff in the water. Okay? And that, in the context of what I'm discussing here, sometimes referred to as quantum foam. And what it does is it reflects something that we know about quantum mechanics. Quantum mechanics is the physics of the very small. Atomic scale, subatomic scale, and small. And something that's important to understand about quantum mechanics is it's inherently uncertain. There's a certain degree of randomness and probability when we're dealing with things on the atomic scale that is not so obvious on our everyday size scale. So because of that, our modern theories of physics seem to predict that what you will see in the fabric of space-time on this very, very, very tiny quantum scale, I mean way, way, way smaller than the size of the nucleus of an atom, we're talking very small, that you would see this kind of frothing, bubbling sort of structure to space-time. So the idea is like if this is our flat space-time and we zoom down, we zoom down, we zoom down, we zoom down, we start to see some ripples, and keep zooming in, you see this kind of chaotic, frothing, kind of random, bubbling and jumping structure in space-time. And it's thought that what happened is our universe kind of grew out of one of these little bubbles that kind of bubbled out of this structure. And because of sort of the chaotic and random nature of this, that when a little chunk of this kind of started to balloon out, and ballooning out is sometimes called inflation, when that little structure started to inflate, then what happened is the variations that are apparent here kind of got frozen, and you had some little spots which were less dense, some little spots which were more dense, and then as the universe expanded, you got this eventual. Okay, that's the idea of this. Whether or not that's completely accurate, well, maybe we'll figure it out. We just have to wait and see. Right now, it's the best. It's one of the best ideas that we've got. But we'll see. Now, some other things that I want to mention is that a lot of this stuff is stuff that we have very solid knowledge of. The idea that we have a very good handle on how big is our observable universe. Okay, we've got a pretty good handle on that based upon the laws of physics as we know them and the calculations and our observations. The universe is in steady expansion. Yeah, we've got a good handle on that. We've got many, many independent lines of evidence in that direction. From that, we can figure out exactly the age of our universe. So all of these things are fairly well established. Now, once we get to this point, yeah, okay, we're kind of reaching a little bit of the limit of our knowledge, but we're hoping that we can sort of test some of these things out and figure out exactly what's going on. But at the same time, we have open questions, even more open questions, and we've had very interesting developments in recent decades that lead us to scratch our heads a bit, which is always fun in science, because it's nice to know that we don't have all the answers, but it does lead to more questions, and it leads to more questions that just leads to more inquiry, which is really groovy. It's great. I love it. This is one of the big ones. Now, how many of you have heard about toys?
So that quantum foam theory, that's like a widely held idea?
It's fairly popular among many cosmologists and theoreticians. Now there are others who challenge the notion, but in general, this seems to be thought of as a pretty viable idea. Now again, whether or not it's actually the correct idea, we have to wait for experimental confirmation. Maybe the Large Hadron Collider can give us insight to that or not. So that's why I say we're kind of, we're kind of getting on the borderline of our knowledge. That's,
More than 50% of cosmologists, if I can.
I wouldn't. I don't know if I want to say percentage, but I would say that I would say it's a pretty popular group. I don't know the exact percentage. But there could be almost. You have people out there like, gosh, what's his name? It's not really small. It's I should know that's one of my former students. Is PhD this guy. Not Penrose. Is it Berkeley? He's a string theory guy. Hamburgers, not Brian Green. Susskind, Leonard Susskind. I mean, Leonard Susskind, a lot of people like him they have an idea. It's called cosmic landscape, space and string theory. Then there's holographic universe theory. There's Smolin's quantum gravity idea. And these are all kind of intertwined, competing notions. And they are in some ways related and not related. But
I've even heard that, like, another idea is that black holes propagated.
Right, yeah, that's another idea. Is that that's kind of loosely related to the holographic universe, and very loosely. We're inside a black hole, and so on. Yeah, so there's all kinds of interesting stuff out there. Yeah, but this is the one that seems, at least to me, to be reasonable and more viable. But it's not. They're not necessarily in competition. Sometimes they complement each other. It really just depends on which specific set of theories you're looking at. And this is the thing that theoreticians all argue out in the journals and so on. But what it's really going to take to make a distinction between where are we really going and how do we really know which one's right is, well, eventually you're going to have to come down to doing an experiment and see where that leads. One of the main reasons why I started to talk about this is because it ties into some other things I'm going to talk about in a few minutes with multiverse theory. So I'll come back to that. Now, how many of you have heard about, if you've heard about dark matter, if you've ever heard the term dark matter, raise your hand. Okay. If you've ever heard the term dark energy, raise your hand. Okay. If you know the difference between dark matter and dark energy, raise your hand. Okay, so all right. Most people actually don't know that there's a difference between dark matter and dark energy. Some people use the terms interchangeably. Okay, let me give you just a quick point. These are some of the things that have kind of come up in recent decades, which are kind of new. Well, dark matter is not such a new idea, but it's become more acceptable. But they're kind of new. They're kind of exciting because they kind of challenge things and they throw little challenges into the theoretical mix. So you got to kind of put it all together and make sense of it. The idea of dark matter is this. Very quick way of talking about this. It ends up that for a variety of reasons, we have a lot of lines of evidence for this. But basically, I'll give you the one line of evidence that really kind of set this whole thing off. Decades ago, some astronomers were observing the rotational rate of galaxies, right? Because galaxies, many of them will rotate, not many of them will spin and rotate. And they observed that all these galaxies they looked at would rotate faster than they're quote supposed to. It's kind of like if you have a blob of pizza dough and you're spinning it up to rotate it instead of flattening out. If you spin it too quickly, it can fly apart. Right? Well, apparently, according to observations, these galaxies were spinning too quickly. They shouldn't be held together. So the idea was, well, there's got to be some extra matter that has a gravitational pull that's kind of holding these galaxies together. But you couldn't see the matter in terms of, you couldn't look at it and see it. You could only detect it by its gravitational effects. So because you couldn't see it, it didn't give off light, so therefore it was dark. And because it had gravitational effects, it was matter, so it was dark matter. That's the idea. Okay? And it ends up, we have, like I said, we have a whole bunch of other lines of evidence that point to, it seems pretty clear that there's a lot of this dark matter stuff out there, and most of it, as far as we can tell, kind of, if you imagine that you look at that first picture I showed with all the galaxies in the Hubble deep field view, imagine that there's kind of like a cloud or a halo surrounding each one of those galaxies, and so these clouds and halos kind of overlap, and the galaxies are close enough. Those are sort of referred to as dark matter halos, and it's like most of the matter in our universe is actually stuff that we can't see. If you go through all the calculations and everything, so people say, well, if you can't see it, how do you know it's there? Well, the gravitational effects for one thing. And there are a lot of physicists right now who are trying to conduct, they're trying to actually do experiments where they directly detect dark matter particles. What is dark matter? I don't know. There are some pretty good guesses as to what this stuff is, and you'll hear people talk about neutrinos, WIMPs, weakly interacting massive particles. Physicists love things like that. Anyway, there's all kinds of ideas, but again, it's kind of like the Large Hadron Collider thing. We've got all these competing ideas on exactly what dark matter is, and maybe it's not one thing, maybe it's a lot of different things. We have to keep exploring it, but we know there's something there, and we know it doesn't give off light, so we call it dark matter. It ends up that forms, as far as we can tell, about 23% of the observable universe. And you can see from this pie chart the stars and gas and stuff that we see. Normal matter, we would consider normal matter, this stuff right here, this stuff. That's only about 4% of the observable universe. Well, what's the other roughly 3/4?
Oh, how about percentage?
Oh, no, I'm taking into account your galactic gas. That's about 4%, and the other 3/4, well, this is stuff we call dark energy. So okay, what's dark energy? Well, remember we talked a while ago about the lines of evidence that we talked about the idea of the universe expanding. Okay. Well, I remember I was in graduate school in this, and I don't know where you were when you heard the news, but I'll never forget. I was in graduate school. This is great. This is a great time to be a graduate student in physics. The conventional thinking went something like this. Okay, because gravity is always attractive, right? Whenever you draw something, you let it go, it's going to fall towards the Earth because gravity is an attractive force, right? It's not like, think how weird it would be if I let this pen go the opposite way, right? We don't see gravity do that. And so the thinking was that because the universe is in a state of expansion, our observable universe, we've got all this matter on the inside of the universe, dark matter included, that attracts gravitationally, that as the universe is expanding out, that gravity is going to pull things inwards. Right? It's going to slow down the expansion. This is what most people thought, that the universe would be expanding outwards and the expansion would be slowing down. Well, in 1998, it was discovered that the opposite was true. Now, I'm not going to go into all the technical details about supernova and the distance matter and all this sort of stuff, but the basic idea was there were at least 2 independent investigations that discovered that distant objects were actually expanding away faster than they thought they should have been. And when all the data was put together, it was discovered that instead of the expansion of the universe speeding up, it was instead of it slowing down, it was actually doing the opposite. It was speeding up. And so people were like, okay, all the physicists and the cosmologists start looking at each other. That's funky. What do we do with this? How do we figure this out? What's going on? And well, you couldn't see what the source of this was, so it's dark, and the word matter is sort of taken, and so this isn't really a gravitational effect. It's kind of like an anti-gravity effect almost. It's a repulsion. It's actually pushing things out and attracting it in. So dark energy. And the thing about dark, there's a lot of names. There's a lot of other names. Sometimes it's called quintessence. Sometimes it's called the cosmological constant. There's all kinds of names for this. But really, what it is dark energy, quintessence, cosmological constant. These are all terms that basically are used by physicists and cosmologists to say this is the thing that's driving the expansion of the universe to go faster and faster. And the really crazy thing about dark energy is we really don't have any idea what that is. We can represent it mathematically in our equations. We can quantify it, we can do all that, but we really don't know what it is. And it's even, when we talk about dark matter, it's like, okay, we have kind of a handle on what that might be, we're working on ways to detect that, and I know that there's active research on this, but we are way more ignorant of what that is. So that's an even more exciting question. What the heck is going on? Or as I like to say to my students, WTF, what the physics?
So, vacuum energy. It would work really great, except I remember in quantum mechanics, we calculated what the vacuum energy of the universe should be. It's like this ridiculously large number.
Right.
But if it wasn't, it would really explain dark energy. I always found that fascinating.
Yeah, it'd be so nice if the equations worked out the other way, wouldn't it?
So my question was, is there something wrong with whether you're using quantum mechanics or quantum field theory? Is there something wrong with the equations in calculating?
That's a perfectly valid question. We don't know any. Okay, we're going to get a little technical here in a second because I can detect a physicist here. Bond, right? Modified Newtonian dynamics. That of course was a competitive idea to another matter, and then Bond's going to go on the way out of it because mostly of the season one. I don't know if there's some kind of equivalent. I don't know if there's some kind of equivalent equation in modern cosmology to adjust the equation, so to speak, to account for dark energy. I think really dark energy is still such a mystery. I mean, I haven't read up on the latest on this, but I get the sense that it's still such a huge mystery that people are still trying to figure out, okay, how do we actually research this stuff? So, question mark. Don't know.
It was really, I mean, there is a 0 point energy to space time.
Right. Yeah.
It has to have some value, and whatever that is, shouldn't it contribute to the accuracy?
Don't know.
They don't.
I don't know. Well, I don't know if anybody knows that I don't know, so I can't speak to that.
Because we can create this stuff with Casimir activities.
Right. I don't think this is a Casimir effect, though.
It's not.
I don't think this is Casimir effect, or even really technical. Sorry. But no, from what I understand, dark energy is not necessarily related to Casimir effect. Because as far as I understand, Casimir effect is actually attractive. Dark energy is repulsive in one direction. So.
Well, it could be a cosmic effect from the rest of the universe we haven't seen. It could be pulling it to incorporate.
Who knows? I don't know. I don't know. And again, that's another question. And that's a fair question. I got a clue. So.
Has anybody thought about the effect of our Congress sucking energy?
And we're in that's funny. Anyway, we put all of this together, and what does the future hold for our observable universe? Because that we're observable. Basically, you get three scenarios. We have the Big Bang. Our universe is expanding from its primordial state, and it could go as far as we know one of three ways. You can get a big crunch, in which somehow dark energy, or whatever you call it, ceases to be such a repulsive effect, driving our universal expansion more and more and more outwards. Maybe gravity takes over and everything kind of collapses. It's sometimes called a big crunch. You get maybe kind of an indefinite sort of equilibrium state where it just kind of keeps expanding at a certain rate. It doesn't speed up, it doesn't slow down. That's the indefinite expansion. And then you get the big rip idea, which is if dark energy continues to dominate, then the expansion will be driven faster and faster and faster. And eventually you get to a point where the space-time is going to expand at such a rapid rate that galaxies will no longer be able to see each other because they'll expand away so fast that the light coming from this galaxy can't even get to us because the expansion rate is actually faster than the universe. And eventually you get galaxies themselves being pulled apart, stars being pulled apart. Big rip, right? Everything gets ripped apart, leading down to the quantum level. Who the heck knows which of those is going to end up happening? Now, remember, everything up until this point in the talk is kind of about our observable universe. Okay, this is where we really start to, in my opinion, get into some. Up until this point, we've been talking about hard science and stuff. Now we're starting to. We're still going to talk science, but now we're going to start to transition to a bit more speculative science. And whatnot, because now we're going to transition into multiverse theory. So I'll pause for dramatic effect, relax, and take a sip.
is that there are lots of ideas on what's sometimes known as multiverse theory or the theory of multiple or parallel universes. There are lots of ideas of it. And well, what I'm going to do is I'm just going to kind of briefly outline tonight some of the ideas that have been put forth by one of the big popularizers of the idea of multiverses. His name is Max Tegmark. He's a theoretical cosmologist. And he's kind of come up with like a hierarchy or a taxonomy of what are called 4 levels. And I think this is kind of a neat way of thinking about it. Now, there are other ways you can think about this. There are other ideas that are out there, but these are kind of like the most obvious. Now, it's important to understand that we are making a transition now into more speculative physics and cosmology. Okay? And depending upon what we're talking about, some of these ideas may be more speculative than others. And as you're going to see, some of these ideas get really out there. Some of them, actually, once you start to think about it, aren't really that out there. They're so weird that they're not out there. That out there. Well, let's talk about, in my opinion, probably the most plausible idea. When we talk about the idea of multiple universes or parallel universes, remember we talked about the idea of our observable universe, right? We look out in the sky, we see our universe, and the reason why we see our universe is because in the roughly 14 billion years in its existence, the light has had time to get to us. So it's that limit of how far we can see, that limit of our cosmic, our vision with the cosmic background radiation, that's sometimes called the cosmic horizon. Okay? Because we can't see past it because the light from those further distant objects hasn't gotten to you yet. So this is where we enter the idea of what's called the level 1 multiverse. Okay? The idea of level 1 multiverse is that beyond that cosmic horizon, there's more universe that we haven't seen yet. Okay? Now, the thing that's really wild about this is that if the idea of dark energy continuing to drive the universal expansion, say in the scenario of the Big Rip, right, where the dark energy dominates the gravity and the expansion of our observable universe keeps getting faster and faster, then eventually that means that the stuff that's really far away will never see it, because it'll start to, the space-time in between us will expand at a rate greater than which light can travel back to see us, right? So light will never be able to quite get to us. So that's kind of the limit. You can't see past that point. But if the universe is infinite in extent, if the universe is infinite in extent, which is an open question, then if we stop and think about the logical implications of those two things, then that means that, well, in an infinite universe that just keeps going and going, though you can't necessarily see it for the reasons I just mentioned, that means that maybe somewhere out there, really, really, really far away, there's a group of people that look just like us, in a room just like this, listening to a talk just like this, from a guy just like me, except I have blonde hair. And the room goes quiet. And if you really think about the idea of an infinite universe that's infinite in extent, that is a logical conclusion. That you are not the only you, for example. That there's an identical copy of you out there somewhere.
Simply because there's so much stuff out there.
Simply because there's an infinity of stuff out there. Right? I mean, really, if you think about it, if the universe is really infinite in extent, and there's a certain point beyond which we can't see, then there are, in a sense, other universes, right? We call them kind of other universes because we can't necessarily see them, and they can't necessarily see us. But there could be, here we are, talking, here at UNAM, digging it, and getting into all the cool questions, and then, oh, hey, far enough away, there we are again. Yeah?
So how is it expanding faster than light?
That's a good question.
What was the question?
The question was, how could distant parts of our universe possibly be expanding faster than light? And this often goes back to the often known fact of our theories of physics that you can't have anything travel faster than light. Right? The caveat there is you can't have, according to our current understanding of physics, you can't have anything traveling faster than light through space-time. What I'm talking about when I talk about the universe expanding is I'm talking about the expansion of space-time itself, right? So go back to the example of, like the galaxies are little raisins in the dough, the doughy bread, right? You can't have those raisins move through the bread like little bullets faster than light. But the bread itself, the dough itself, can expand faster. That's not a violation of relativity. Okay. So does that make sense? That's a common misconception. So the idea of cosmic, of beyond our cosmic horizon level in multiverse, interesting, right? Yeah. And that's just level one. We got 3 more to go. So if you're freaked out on level 1, wait to see the next ones. Another question.
Isn't it your implication that there must exist a universe that's identical, except for some trivial change like your hair color? But that doesn't necessarily follow just because there's an infinite set of universes. Because I know they did. I know there's like, for example, they show mathematically that like in an infinite, like say the number of pi. If you were to expand it, infinitely expanded, it doesn't necessarily contain any possible sequence, every possible sequence of numbers that you can envision. In other words, it's not necessarily the case that because it's infinite that that's unique. That every possibility has to be represented. They've actually mathematically shown that that's not the
Right.
case.
Every possibility doesn't necessarily have to be represented, but I think somebody who would.
It's actually something I've always thought when people talk about these.
I think somebody who would advocate for level 1 multiverse would counter that the opposite is not necessarily true.
Sure.
Right. So yeah, and then that's where we start kind of running up against it when you start talking about. This is where you start running into problems with the idea of the multiverse, because now you're talking about looking or thinking, speculating. Right? Remember, it's important we're talking speculation right today, and I have to emphasize that again and again, guys. When we're speculating and thinking about this, it's important to understand that we're talking about beyond the confines of our observable universe. Right? So this is where things start getting more uncertain, start having disagreements like that, which are perfectly valid disagreements. Just because it could happen doesn't necessarily mean it has happened. I don't know, right? But it's an interesting point. But I
think part of the premise is that it's a random variation. So physics is the same across all these universes, but there are random variations in initial conditions.
Whereas the calculation of pi is not.
Well, yeah, but and I haven't brought up a good point that I haven't gotten to mention yet. It's important also to understand when you talk about a level 1 multiverse like this, we are saying that the laws of physics are the same everywhere. This is not like gravity is an English cube law. So that's what we're going to next. Another question.
I just wanted to clear up the idea that the identical parallel universe is separated by space and not necessarily the concept of the Poincare recurrence of the universe.
Can you clarify what you mean by Poincare recurrence?
So the Poincare reoccurrence, so there's a theory that given the same amount of matter and energy in a space, that is going to disperse, but eventually end up at the exact same space that it started at. And supposedly that's been calculated to be for our universe that all matter and energy is going to return to its original space in 10 to the 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 1.1 years. And that the universe supposedly resets itself. But you're talking about something completely different.
Yeah, this is not that. This is not that. Yeah. I understand what you're getting at, but yeah, you're right. This is completely different. So this is the idea of level 1. Okay, now let's go talk about level 2, where things start to get even more interesting. Universe that was the result of another bubbling out of this quantum foam, and sometimes this is called the vacuum state, right? And this is the same basic kind of idea that we're getting technical in. But that's the idea. And so what you get is you get this kind of almost, and then sometimes maybe you could get universes bubbling out of other universes according to this idea. You could get a birthing of universes out of other universes or whatnot. And maybe these universes have different fundamental constants of nature, depending upon the initial conditions of the space-time structure when it kind of bubbled, so to speak, and inflated. And those physical properties of that universe, of that particular universe, are set, just like particular physical properties of our universe are set when it bubbled up. And so you could get different bubbles having like different properties of different physical constants of nature, maybe different laws of physics. Maybe here gravity is an inverse square law, over there it's an inverse cube law, right? Weird. Okay. And so this is kind of another way of looking at this, so to speak.
Why do some of the regions stop? I'm not clear about it. Why do some of the regions stop expanding?
Because since you have potentially different initial conditions, the idea is, okay, so in our universe we've got dark energy, right? And from right now, it looks like our dark energy is dominating over gravity, right? So it's driving quicker and quicker expansion outwards, right? But because you're getting different initial conditions, this theory goes, when those little other bubble universes kind of popping out of that vacuum state of the quantum phone. Because you're getting different initial conditions, maybe in those other universes there is no dark energy, or maybe it's weaker than in ours. So gravity dominates, and so that whole universe, that universe expands out and eventually stops and collapses back in on itself. So that's the idea. That's the basic thinking, I guess, behind this thing. Yes?
So I recently read an article that talked about how they mathematically correlated an idea that didn't seem to make sense to a possibility that the majority of dark energy is made up of gravitinos. Gravitinos, I believe.
Yeah, I haven't heard that one. That's a new one to me. So, okay. Yeah.
And also, I had read that neutrinos are actually are considered dark energy or dark matter.
I know that at one point neutrinos were a candidate for dark matter. I think that I'm not sure what their status is currently on that. I don't know if they've kind of been that question's been settled yet, because there's a lot of neutrinos in the universe. Now, this is the way you have a level 2 multiverse. Okay, so I think as we kind of go up the taxonomy, things get a little stranger, and things get, I think, a bit more speculative, a little more questionable, but interesting. Okay, so again, it's important to remember we're speculating based and extrapolating based upon our current understanding of science and cosmology.
Before we move on,
Sure.
so level 2 multiverse. Would this also encapsulate the idea that you could have a universe on the bubble of another universe?
Yes.
Okay.
Yeah, that's what this picture is.
Okay.
Yes, do that. All that is level 2. Okay. All right. So now let's go even stranger. This next one's kind of my personal favorite because I love quantum mechanics. Okay. Do you remember when I stated earlier that quantum mechanics, it's the physics that we use to describe the universe at a very, very small scale, subatomic scale and everything, and there's an inherent property to quantum mechanics which is random and based purely upon probability, right? So if you're talking about making measurements in this sense, you can't necessarily always count on getting exactly this result. Like with classical physics, what we call Newtonian physics, it's very deterministic. In other words, for exactly the same initial conditions, you get exactly the same result every single time. Well, in quantum mechanics, it doesn't work that way. In quantum mechanics, you have the same initial conditions, but you might get a slightly different result, and it's all probability based. So there's a lot of the way many people live is it's called indeterministic, or maybe a lot of people think this is kind of random stuff.
You raise your mic.
Sure. I'm sorry. The idea of a level 3 multiverse is it has to do with what's called the many worlds interpretation of quantum mechanics. There's a lot of ways that you can interpret quantum mechanics. There's the Copenhagen interpretation, there's Bulgarian quantum mechanics, there's hidden variables, there's all kinds of things. And then there's the many worlds interpretation. Now, the many worlds interpretation is an interpretation that to many physicists, not all physicists, but to many physicists, it's a satisfactory interpretation because they consider kind of mathematically elegant. It seems much more simple mathematically to many physicists than the other interpretations. It seems to solve some problems in quantum physics that other interpretations bring up, like the coherent interpretation, wave function collapse. If you're a physicist, you want to be in. Anyway, the basic idea behind many rules is this. Take, say, some kind of event, there's a die rolled. This is just an example. You roll a die, and it could come up 1, 2, 3, 4, 5, or 6. If it comes up 1, well, there's 1 out of 6 chance, there's a certain probability you get the number. Okay, you get that result because this is the universe where that happened. But there could have been a 2 that came up in a parallel universe, and a 3 came up in another universe, and a 4 came up in another universe. And so what happens is when you talk about the idea of many worlds or a level 3 multiverse, and you have to understand that this is independent of the other 2 ideas we just talked about. This is a completely different idea. That the universe, in a way, is kind of, I don't like to say it this way, but it's the best way I can popularize it, that it almost kind of branches off and follows different paths. Right? So when you roll the die, if a 1 results, that's in this universe over here, and the 2 here and here, and they all kind of branch from this one universe when that event took place. And then every time there's some event that's kind of random in a sense due to quantum physics, that leads off to another universe, and so it's kind of infinitely branching in this sense. So a way of, and so that leads to ideas of parallel universes. And so here's a way of looking at this. I actually stole this, I think, from one of Max Tegmark's papers. Here's a way of thinking of this as a way of distinguishing it from like a level 1 multiverse, for example. So in level 1 multiverse, it's like, okay, here you are, and you're asking this nice person out to go for a drink. Would you like to go for a drink? And he or she says, I'm sorry, I'm too tired. Okay. In a level 1 multiverse, really, really, really far away somewhere, the same conversation is taking place. Would you like to go for a drink? But then the person says, oh, okay, let's do that. Right? And both are happening in the same huge multiverse, right? Because of the reasons we talked about, you got an infinite universe and so on. And there you go. Okay, that idea. A level 3 multiverse, and of course that could be nested in a level 2 multiverse, just like we said. So a level 3 multiverse, the question was, would you like to go for a drink? And then at that point, there is kind of a split in the universe, and then 2 other universes are created, where in one universe the individual says, sorry, too tired, and then they go their separate ways and never interact again. And then the other universe says, oh, sure, let's go for that drink, and then they end up getting married and have kids. Okay, so that's kind of the idea. But an important thing to note, and I should point this out because this gets into a bunch of statements. Sometimes a lot of people think that the idea of a level 3 multiverse necessarily implies the idea of human choice. We're not necessarily talking about that. We could be talking, instead of talking about asking people out on dates and stuff, we could be talking about, like, okay, does this atom decay at this particular moment, right? And if this radioactive nuclei, say, decays at this particular moment, that leads to the universe A. But if it doesn't, that leads to the universe B, right? It doesn't have anything to necessarily do with like human free will or choice or anything like that. That's an important point to know. Yes.
I just wanted to add that the most succinctly way that I've heard this put is that the universe is a multidimensional Cartesian product of every possibility of all the matter and energy that it consists of, except where the quantum probability is equal to 0.
Okay.
That's the most succinct way I've heard this what is universe splits. But your way's good. Yeah, your way makes sense too. It makes sense to me. It's like, yeah.
I have a suggestion. We should forbid the use of foaming soap anymore.
I'm not sure that's
dangerous.
Okay, so he talked about it in a very abstract concept. But like, how would you explain this in a like, concrete, physical? If level 2 is like, the bubbles of the quantum field, I'm trying to understand this in a physical sense. I understand it theoretically.
Okay. Let me give it to you in a sense that will maybe make sense. Okay, here's an example to kind of have it make sense in the context of level 2 multiverse, kind of tied to that. Right, remember we had the idea of level 2 multiverses, you have these little universes that kind of bubble up here, bubble up there out of the vacuum state, or the quantum form, or whatever they want to call it. Right? And then they go about their own ways, and sometimes they lead to other universes. Sometimes they go, oh, we're going to die, and whatever. They do their own thing. They go through their own evolution. According to this idea, you could have, it's a difference between, okay, you got this level 2 multiverse, and these little baby universes are kind of bubbling out. Well, here's baby universe A, and it bubbles out, and it goes on, and it births more universes. But that's a random thing, right? It's based on quantum mechanics. So that branching point is, does baby universe A go on to birth other universes, or does it just kind of go this way and go, but,
So it's all
right.
happening at the same time.
Right. Yeah, that's, yeah. Yeah, that's all just kind of weird.
So I guess
It's very hard to wrap your mind around.
I guess now I just don't understand the difference between this one and
Level
level 2.
2 is kind of looking, level 2 would be looking at one branch and following it,
Okay.
right? Level 3 is saying, okay, we have all these different branches and we're thinking about all these possibilities. I probably just flashed something. But that's okay, none of you were studying doing it at all.
I can sort of see how, at least in principle, level 1 and level 2 could be, the observations could be tested. Is there even a theoretical way that the existence of level 3 could be tested?
We're actually going to get that in a few moments because, again, if we're going to talk science, right, you want to talk about the prospect of testing and empirical analysis and stuff. And we'll get to that question in a second because these all have their advantages and disadvantages. So to some or others, in my opinion. And then, of course, on the next tag mark, or at least small. You got a question?
Well, could we try to explain all this if mathematically we could grab a fistful of sand, and as part of that fistful of sand we had gas, different magnetic charges for each particle of sand, we had wind and all kinds of things, different polarities, different molecules within each gram of sand. You just threw it all up in the air, and all kinds of things could happen, just as all kinds of things could happen if you splashed water on the floor. So bubbles can come together, or the bubbles disperse, or the bubbles dry out.
The only problem with that, again, this is getting back to this gentleman's point, I think, is anything that we would observe from that phenomenon, we're in that same universe, right? So we're kind of going along that branch. So the question he's getting at is, how would you know that this branch even exists if you're stuck in this one? That's kind of what you're getting at, right? And that's where you start to get, that's where it starts to get really tricky. All right, but before we do that, let's talk about the last level, level 4, because, and you talk weird, this is where we get really weird. And in my opinion, this is where we start to get really philosophical and metaphysical. Because basically what Max Tegmark proposes in level 4 multiverse is that the best way I can think to say is that math is reality. Okay, this is sometimes called radical Platonism. Anybody who's studied history of Greek philosophy knows that Plato, he literally kind of made part of his philosophy that math kind of derives reality, and everything's mathematically based. This is why I have a picture of Platonic solids. This is one of the reasons why the idea of level 4 multiverse is called radical Platonism, because it basically proposes that not only are we using mathematics to say describe the laws of physics, but or describe reality, but that math actually defines math is reality. This is incredibly abstract. It's so abstract that I can't even give you a picture. That's why I threw this up there. I'm like, how do I think of this in terms of a picture? You can't even put a picture on something. Okay, Plato's solids. And some variations, some people who ponder this idea like to think of it as, maybe it's like a powerful supercomputer, which then you start getting ideas of the Matrix and stuff like that. It's just and to me, this is like the most speculative, and least scientific, and most metaphysical, and most scientists do ask, or even philosophers would agree with that, because this gets into the question, well, how do you test this all? Right, and I don't think there's a way. I think Max 10 might agree that there's a way. I don't see it. I think most people don't see it.
Well, at the molecular level, isn't this what the movie Pi proposes?
I don't know. I haven't seen the movie Pi.
Well, it proposes that there's a mathematical formula to the structure of every molecule. In the
well, no. This goes a step further. We're not talking about using math to describe nature. What this is saying is basically that math is nature. That's basically what this is saying.
So it's basically saying every mathematical structure you could possibly imagine is physically realized?
Yes, essentially that's right. Basically, that's what this is saying.
It's kind of out there.
He said basically that he kind of got it. Basically, what you said one more time.
Every mathematical structure that can possibly be realized, and I wouldn't even know how to actually, that you can conceive is actually realized. And actually, there's some debate as to what do we mean by every mathematical structure that can possibly you can come up with.
And who's doing the conceiving, and then
it's questions.
Yeah, that's right. That's why I say Baker's, that's kind of where you're going with this. Yeah.
I completely agree that the Platonic model doesn't, well, it just doesn't make sense, logical sense, but it is one of the three different philosophies of math. You have the Platonic model, the nominalist model, and the fictionalist model. So nominalist says that the numbers pretty much just are things that we use to describe things. Fictionalism says that numbers are convenient fiction. We use that to help us approximate things. But the Platonic model says that numbers are real things and they exist in and of themselves, and that's just...
Yeah, math is real, and this is basically... Yeah. Now, let me get to that point that this gentleman talked about, testability, plausibility, and so on, because this is a valid question, right? So you say, okay, what about plausibility of the multiverse? And I know there's a lot of text here in the presentation, so I'm just trying to post on there. Pages full of text, but I couldn't find any decent pictures to go with this. I tapped myself out once I got to the Platonic solvents. Level 1, among scientists and cosmologists and people who kind of talk about this stuff, this is the most non-controversial one, but there are still loads of questions like this gentleman question. It seems like it's the most logically sensible result if you extrapolate from the idea of a universe that is indeed infinite in extent. In the sense of talking about multiverses at all, I mean, this is the easiest to support, but it's still weird to think of the idea of there being an identical copy of you out there somewhere. That's strange. And then this gets into all kinds of funky questions about free will and determinism, because if there's an identical copy of you out there, then are you really doing what you want, or are they doing it, or who's the real you, and all this sort of shit. This is stuff that this is the stuff that drove me to not only love physics but now I'm starting to deal with the philosophical questions. That's really great. A bunch of philosophers around the table that you go all in and stuff like that. Level 2, what level 2 has going for it is the basic idea seems to be pretty consistent with our modern theories of cosmology, that is modern theories of inflation. It seems to be consistent. It doesn't necessarily mean that it's an accurate view. It just doesn't seem to violate that idea. It could serve as a possible naturalistic explanation for the idea of fine-tuning, that the universe just seems to be made for us, so to speak. We'll get to that in a few minutes. There is some evidence that's disputed, depending on which cosmologist you talk to, that there's this idea of what's called a cold spot in the cosmic background radiation. There's idea of a cold spot that is one of those big dark blue blotches that maybe that is evidence for this, because the idea is that, okay, if you, and these are really accurate, is that if you have these bubble universes that are somehow adjacent to each other, if somehow in the higher level multiverse state, higher level 2 multiverse, if they kind of rush up against each other, that might be visible somehow in our cosmic background radiation, but then a lot of that's disputed. So maybe that's a way to test it out, maybe not. It's an argument, a lot of argument on that. Level 3, we're going to have a lot of the single speculation. the idea of many worlds is perfectly consistent with quantum mechanics. It doesn't violate quantum mechanics. It's a mathematically pleasing interpretation of quantum mechanics for a lot of physicists. However, the question of testability is really, how do you do that? Nobody knows. I don't know if anybody has a good idea. So then we're really kind of stretching things, right? And then you get to level 4, and what the hell? I don't even know what you do with that. And because of that, a lot of scientists and many people consider it's far too arbitrary and metaphysical to be calling it science. It's not even called science. It's just it's Platonism, right? And so that's kind of the standpoint on the plausibility question. Yeah.
It is actually my understanding that they sort of verified with experiments, like high energy experiments to attempt to violate causality. They found that the Novikov self-consistency principle pretty much holds up, and something always goes wrong. So suggesting that when you attempt to create a situation with a quantum probability of 0, it can't happen. So that kind of proves the multiverse sort of.
Well, which aspect of the multiverse is the question? Which one? I don't know.
Well, like the Everett Wheeler interpretation.
The what?
The Everett Wheeler interpretation.
Hugh Everett. He's the one that came up with many worlds.
Right.
Yeah. So I don't know. Yeah, me. So
It's interesting stuff.
a lot of dispute on that. Okay, so I've only got 3 slides left, and this is where we. Okay, not actually 4 slides. Like 4 slides. Pause and think for a second, right? Because at this point, I see a lot of people kind of thinking about this stuff, and so. I wouldn't be surprised if you start looking at me saying, gosh, is this guy even serious, or is he high? High? What's going on here? And I think at this point it's a good idea to pause and consider something that I found this great quote in Scientific American magazine that was really getting into some of the things that we're kind of chewing on right now, because we are getting terribly speculative at this point. Terribly so. And I'll just read this very quickly. This is from George Ellis. You wrote this in Scientific American, I think, in 2004. I can't remember exactly. This is a skeptical as I am. I think the contemplation of the multiverse is an excellent opportunity to reflect on the nature of science and on the ultimate nature of existence. Why we are here and looking at this concept, we need an open mind, not too open. It's a delicate path. Parallel universes may or may not exist. Right? The case is unproved. I agree with all of this. We're going to have to live with that uncertainty. Nothing is wrong with scientifically based philosophical speculation, which is what multiverse proposals in large part are. But we should name it for what it is. Right? And I think that's really, in my personal opinion, I think it's really good to think about this, because we are kind of on that borderland of what is testable, what's not testable, how much is speculation, how much is really grounded in those scientific things.
First of all, I'm sorry for monopolizing the questions, but I'll try to make it brief. Basically, in quantum computing, we are able to use the superposition of qubits, quantum bits, in order to actually do work. Doesn't the fact that those superposition states, the fact that they're able to do work, doesn't that prove that those other realities exist?
No, it just proves this one exists. Right? Because how would you know that another reality exists? Or that how would you be able to? There's potential in the equations that another reality could exist. How would you know that? How would you experience it?
Because the way that the quantum computer works is that only the correct answer will collapse the wave function and give you the right answer.
But when you talk about the idea of collapsing the wave function, okay, we're going to be really technical here in a second. Let's talk afterwards, actually, because once we start talking about getting the wave function collapse, carbon high interpretation, all that, we're going to get way too technical, I think. So let's hook up afterwards, because I think I know where you're going, and I got a way I want to talk to you about it. It just deviates too much, but I think that's a fair question. Okay, so I've only got a couple of slides left here. So since we've gone down the philosophical rabbit hole, which I love to do, let's just get in there. Let's get on that, right? Okay, so I mentioned this briefly before, right? You'll run into some people. One of probably the most famous contemporary examples is someone named William Lane Craig. He's a philosopher. He's a theist. He's a god. And he has argued that the idea of the apparent fine-tuning of our universe is an argument that God exists, because the reason why we're here is because the physical constants of our universe are just right so that we can exist. So, you know, if for example, one of the counterarguments is that if the mass of the proton were just off by 1 or 2%, then we wouldn't be here at all. Or if if the fine structure constant were off by 1/1000th, we wouldn't be here at all. And you can just do this with any of the physical constants of our universe. Take your pick. And this idea is broadly wrapped up in something called the anthropic. That's a very broad term, but that's basically the idea. In other words, we're here, the argument goes, we are here because God created the conditions of the universe such that we would be here. Okay. Now, there are, in my opinion, a lot of problems with that argument. The one I'm going to focus on here has to do with multiverse. If you think about the concept of, say, level 2 multiverse, right? This is the idea where you're having these, where all the universes form in a vacuum, and they can have different physical properties and so on. Then, when you look at it that way, well, this whole question is moot. It basically says, okay, because we're here, because our universe just happens to have those properties, and there are plenty of other universes where those properties wouldn't exist, and so we don't exist in those other universes because we're here. Because our universe has properties, right? And so it's a naturalistic explanation that doesn't necessarily require a God. That's the counterargument. This is really interesting because even if you were to not talk about the level 2 multiverse at all, which again is speculative, of course, into the God question, there's a lot of speculation there too. But let's suppose you get rid of the idea of, not get rid of the idea of level 2 multiverse, but let's maybe expand on it here just a touch. You say, okay, what often happens when people like Craig bring up the anthropic argument that, if this were just off a little bit, we wouldn't be here, is in many cases we'll only look at one constant nature at a time. Right? Now, if you think about the idea of a level 2 multiverse, right, there's nothing that says that, okay, well, we get universe A and it bubbles up here, it has all the same properties as universe B, except the mass of the proton is off by 2% here versus here. Right? There's no reason why you have to vary only one variable at a time. Why could you have different, many variables changing simultaneously, right? And the interesting thing is, I stole this from an article in Scientific American, and actually did calculations on this, speculative calculations. And it's really cool. You take properties of the universe, you stick it in a computer, you play with the numbers and see what happens. And finds that basically, if you think about the idea of changing more than one variable at a time, you find that there are potentially many more universes that could be hospitable to us, life like us, right? So, and then this makes you say, okay, well, how fine is fine-tuning, right? I mean, if it's not really that fine-tuned, then it kind of undercuts the whole fine-tuning argument, right? So if you have one variable and you vary a little bit, you're going to say, oh, well, if you go beyond these bounds, then that's it, we're done. Well, okay, you vary this variable a little bit. What if you vary both at the same time, and you then suddenly start finding, oh, there's a lot of potentialities. And so once you really start to kind of absorb the, I think we've kind of shown there's at least some more plausible than others explanations that could be invoked, which are naturalistic, not required necessarily the implication of God. And so with that, I come to my very last slide because it's about life, the universe, and everything. I guess we can just jump straight into question and answer now. So fire away. Yeah, go.
Just on your last slide.
Oh, the sexy one? Okay.
Yeah, first of all, how does this whole thing work?
Wait. You want to know how that works? That's an entirely different talk.
Now that the stork is out, I'm so lost. Lastly, I was wondering, but what is sort of the anthropic, sort of like the naturalistic anthropic idea? Wouldn't that even be possible in a single universe? I mean, if the universe is finite in time and like presumably has some sort of ending, and I would assume that that could then spawn some successor universe where that's tuned for a different species. I guess I'm saying
there are models.
There are models of the multiverse.
Yeah, that's true. And there are models of. That's a good point. There are models of universes, singular universes, where one universe can last or like another one, and then maybe the properties of that subsequent universe are different from the previous one. And there are some models out there now. I'm not necessarily to speak for this because I have research enough to talk about. Inconceivably under those kinds of models, that's a naturalistic.
Well, I guess my other thought is that I'm also kind of curious about, like, there might be sort of a viability issue. Like, there might be certain combinations of physical constants that cannot form a universe.
Or a life-sustaining universe, right?
Right.
There's no doubt that.
Right. So in other words, it's anthropic only in the sense because, like, the universe would never have gotten to a state, even maybe a state of, like the formation of atoms. And so, like, in other words, like, that possibly may have been tried and sort of failed.
Yeah, well, and that kind of gets back to the idea of, well, if you have this idea of multiple universes, then there can be a whole bunch of failures out there and only just a few successes. You can look at, there's a good analogy here. What is it? This is kind of interesting, I think. It's like, I don't know, I'll make an analogy from my teaching experience, right? You got a lot of kids in a graduating class, right? And there's only one that's going to make it to the valedictorian, right? So that one success, there's a lot of kids that don't make it, right? And the kid who ends up being valedictorian could say, well, I'm here because God wanted me to be here. Well, it kind of screws the rest of the kids up, That doesn't necessarily stop that thinking from the naturalist's mind. Another way of thinking about the anthropic principle is kind of along the same lines. It's like, we're here because God wanted us to be here. Okay, well, if God really wanted, and then that leads to other philosophical questions like, okay, well, if God wanted the universe to be used as life, how come it's not everywhere in the universe? It's like here. And that leads to other challenges and so on and so forth. It's worth noting that there is a naturalistic variation on the anthropic principle. I think it's called the weak anthropic principle.
Yeah, that's right.
Yeah, and it's basically saying, okay, it basically essentially says, okay, we're here because we're here.
Well,
That's essentially.
But I thought more precisely, I thought the weak anthropic principle was that it's sort of not useful to consider universes that don't lead to us because
we're not there.
Yeah, because we're in the universe that allowed us to be.
Yeah. So.
And one of the ways that I think is especially fun to look at it as is the following: if this universe couldn't give rise to life, we wouldn't be here to talk about it. So it's not that the universe is tailored to give rise to life because the universe is really good at making black holes. The universe is really good at making a lot of things, but not necessarily life. But the fact that life did arise doesn't speak to any kind of creation of the universe. It just speaks to the fact that
there's not necessarily like an elegance to the universe because it took.
Yeah,
there was not.
I remember I was arguing with some people. I just got into taking philosophy of religion class this semester, and I was arguing with some people in the class, and they were trying to make Craig's anthropic argument. And basically, what they were saying was something along the lines of, well, the universe is created for us, and so on and so forth, or the Earth is created for us. I think is the argument. I said, well, yeah, we haven't been around that long. How do we know the Earth hasn't been created
there's still going to be here. So, I mean, so the problem, the other problem with it, it's kind of the anthropic style argument is you can turn it around like this.
Like why did she injury here's the creator?
Yeah, that's the other problem. It's like, or as I said, if you want to make it that argument, then why can't you just turn around and say, well, the universe is created for non-life, or it was created for death, it was die. There's a lot of ways. So it's questionable those senses as well. In my opinion.
I hate to shift it back to something more practical, but
Sure.
when I took quantum mechanics, I asked about many worlds interpretation and the Copenhagen interpretation. I was just told to shut up and calculate. But now is my chance to ask it. With
I can't promise the answer.
with the many worlds interpretation, where you have the universe splitting into two copies of itself, how does that square with, say, conservation of energy? Are you actually making copies of the matter, or is it a superposition of states?
I don't know. That's actually not the same question, right? Because the problem is, if you talk about the Copenhagen if you talk about the Copenhagen interpretation, you got the whole problem of what's the mechanism of wave function collapse.
Right.
What's the well, many worlds, there's no problem with that. But the problem, then you run into this issue theory. So, or do you not? Because I don't know. I haven't really answered this question. So help us out.
There's no problem with conservation of energy because the universe is pretty clone. The clone has its own laws and its own history, which is so all the clones have the same history, but they all have the same energy. They all have the same physics. It's just that they have a different outcome for that event.
Okay, so you're not violating conservation.
You don't violate it.
Okay, yeah. Yeah, okay. That makes sense.
Now with the bubble universes.
Level 2?
The level 2, where they're just spontaneously coming out of a quantum foam. They expand into a universe, presumably with perhaps as much stuff as we have here. That's a lot of matter and energy. Where does the energy for that come from? Inflation. That's all from. So this big sea of energy that's already out there.
There's also a very important theorem in physics called Multiverse Theory.
Yes.
Oh, yeah.
It says that conservation laws come from symmetry. So the conservation of momentum is a result of the fact that our laws of physics are the same no matter where you are in space. The conservation of energy comes from the fact that laws of physics are the same no matter what time, where you are in time. But at the singularity at the beginning of the universe, you no longer have that symmetry of motion, movement, or time. You can't go back before the beginning of time. So energy actually doesn't need to be conserved.
And that's called diffuse symmetry breaking, right? At that point, you're getting symmetry breaking, is that right?
Yes.
Yeah, that's what's commonly referred to as symmetry breaking.
Well, I don't know if it's symmetry. The symmetry doesn't hold that.
Yeah, the symmetry doesn't hold there. And then to pick up what I was talking about, the idea is that when you get these little bubble universes butting up, I'll just say symmetry breaking for lack of a better term. Those are the moments when you get that symmetry breaking, and then you can get those sort of apparent revelations of things like energy conservation and so on. And I'm glad you said something about Noether's theorem because I never heard pronounce that right. But you get these pairing of variables, so that's where you get momentum pairing with position, that's where you get energy pairing with time. There's a rotational one too, and I can't remember that one. Angular momentum with what is it? Angular displacement.
Yeah, rotation.
I can't remember. Yeah. So that's so it seems like it would be a violation of energy conservation for those reasons. It's not, but I think another way to look at it too is when you're talking about the level 2 multiverse, the bubble universes, and you're talking about something like a conservation of energy law. Well, that's the law of physics that is contained within that universe, for example, right? And now what we're doing is we're talking about something, so to speak, for lack of a better phrase, external, right? So this is kind of
that's the way I.
Yeah.
Conservation energy isn't violated because conservation energy only applies on like a per universe.
Yeah, it is itself a law of nature that applies to those universes that are created or evolve or whatever you want to call it.
It depends on your models. If you have inflation, there's some potential that's causing the inflation.
Right.
So you could create an energy preserving multiverse.
Yeah, I can see that too. And once somebody talk about the consequences, that gets even weirder. Question?
I just actually wanted to share an interesting factoid that I learned recently, and that is that of working physicists, 42% of them subscribe to the Copenhagen interpretation of quantum mechanics. That's the majority of.
But they should go to jail.
I don't think I was one of the 42%.
Right.
That's how I felt.
It's really interesting because here in the U.S. and in many schools they teach the Copenhagen interpretation.
Right, that's what I learned too.
What is the Copenhagen interpretation?
The Copenhagen interpretation of quantum mechanics, as we keep throwing it around. How do I do this in a brief, quick way? The reason why I think the Copenhagen interpretation is taught is because, okay, first of all, quantum physics is really freaking weird. Okay, if you haven't figured it out, it is so odd, it's so weird, and even for people who study it many times, like some of us, a few of us in the room have, it's very, very strange because it's so outside of our everyday experience. Okay. And so the Copenhagen interpretation, I think, was popularized because it kind of gives you a nice visual way of looking at quantum mechanics in the sense of you look at what's called a wave function. Because we all picture waves, and in physics, waves are kind of nice thing to study because they're well behaved, and they have these nice deterministic waves, and have these cool equations that can describe. And basically what the Copenhagen interpretation does is it describes quantum physics in the context of this wave-like idea called a wave function. And you do a lot of, and it's very pictorial, you get all these really cool pictures and everything. I love learning the Copenhagen interpretation because it really helped me. But the problem with the Copenhagen interpretation is it kind of invokes some things which are questionable. Like one of the big bugaboos is this idea of wave function collapse. So the idea is something like, okay, so suppose you've got, there's this phenomenon of light called diffraction, right? So suppose you've got like a little tiny slit here, and you shine a laser beam at it, right? When you shine a laser beam at it, if the slit is small enough, the light will spread out on the other side, right? Well, if you think about light as a wave, right, how can the wave kind of spread out, yet maybe like a single photon or particle of light end up at a certain spot? Because if you actually lower the intensity of the light enough, so you have one little photon of light going through at a time, you actually eventually get the wave-like diffraction pattern, but only a little piece at a time, right? So a photon actually does land on the screen in a specific place. So how can you have a wave that's spread out that lands on the screen in a specific place? This is where you get the idea of a wave function collapse, right? Going on interpretation is, you have this wave that spreads out, and then when it interacts with their screen, the wave function collapses to this point and gives you this big measurement or this big result. This is a real quick review. The problem is what's the mechanism for that? And this is a big problem in trying to interpret, well, what is that mechanism? Because I've never really heard a good proposal for that mechanism, and so many different interpretations of quantum mechanics that don't even invoke that at all.
So it's basically a more deterministic approach?
Yeah, well, that's another thing that's kind of pleasing in a sense about the Copenhagen interpretation is it is kind of viewed as a bit more deterministic and a bit less nasty in that sense. But it should also be noticed that many worlds is pretty deterministic too, from what I understand.
Actually, Copenhagen is not.
What's not?
What in quantum mechanics, you get states which are mixed states, which are it's counterintuitive to us because usually like the chair is either open or it's folded and so on at the same time.
And those are called superpositions.
Right, so you can get superpositions of states where you can get a particle that is both simultaneously, let's say, spin up and spin down at the same time. And if you sort of take that to an extreme, you get Schrodinger's cat, an experiment where the cat is both alive and dead at the same time. But so in the Copenhagen interpretation, what happens is making an observation. Since you can only observe the cat to be either alive or dead exclusively, one of the two, it's making an observation that forces it into that state. So before it was in mixture of the two. Now it's in one or the other. And you can't, there's no way to determine which way it is. And it's non-deterministic in the sense that you don't know until you make the observation. In many worlds, it's deterministic because it's actually both. Both you observe it to be alive and dead, but just in different universes. From our perspective, it's non-deterministic, but from the physics perspective, it is.
From the multiverse.
The problem with Copenhagen interpretation is that it privileges conscious observation. Like a lot of people interpret it to be, oh, it's a person making the observation. But it turns out that even if you just have a model of quantum mechanics where you have interacting states, large, like macroscopic states can't be in superpositions, just statistically. It just won't happen. Like you won't have a cat both simultaneously alive and dead. It's going to be one or the other just by statistics.
Yeah, because essentially because you got too much matter. You're sort of with the math.
So you call it incoherence.
Right. Right.
Just on that, like, so is that saying that until it's seen, then it's either it has like when it's seen, it's either alive or dead?
Yeah. What I was getting at, and this is where physicists like Ivan and me and some of the other people, this is where I feel back or I think start having connection physics before we have the consciousness question. Because the thing is, people say, oh well, and this is why I made the point, going back to many worlds where, remember I said many worlds, like in Tamar's little picture there, it's like, you ask the person out and they say yes or no. I said, but you have to understand that that's not a conscious human thing necessarily. It's like you can talk about whether or not it's application, right? That can split the universe, right? And then the level 3 interpretation. This is exactly the same point that I was making. That, if I set up that swing experiment with a laser, right, the whole point is you don't have to physically be present sitting and watching it to see the result. You can set up a computer or a phosphorescent sheet or something, just let it run on something. You're not even there. You're not even there consciously present and watching it, and you still get the same results as if you were, right? That's the whole point behind this. That's
so
the
the theory is that whether you're there or not, it's still happening.
Right. The whole point is you'll get the same, similar kind of results. You'll get that result with or without a conscious present. That's the whole point that he's trying to make. He finishes all that. And in the interpretation of the Copenhagen interpretation, you're always hearing about observers. The observation is leading to the wave function class because of the limitations of our language. We talk about the observation that implies observer, and then observer implies consciousness, and that's what people mix all this stuff up. And that's what makes this kind of question.
Yeah, I wanted to ask because I observed this experiment on the two slit, and what I understand as what is so weird is that if you are throwing one photon at a time, you still have the pattern of interference. But for some reason, somehow, you know which slit each atom went through, the interference disappeared. Is that true? I mean, is that what's the difference on the...
What do you mean if you...
It is for whatever method, because of computer programming or something, you know which way it's able to reinforce, making the pattern of the wave. But if for some methodology you use that you know which slit this photon went through, then the interference disappears, and then you see two lines of light.
And I don't get how you would convey that knowledge to the photon. Like,
Well,
I don't
that's
get
the
how
point.
this, like,
That's the
intention.
point. That's why it's so weird.
Well, no, I don't understand the experiment you're
Yeah, that's what I'm confused about. I'm not.
So,
do you understand what you're saying? I'm not sure I get what you're saying.
What you do is, if you just had if light was a wave, you'd get the interference pattern. but we know that light is made of photons. So you can keep the frequency the same. You can turn down the intensity so that it's effectively 1 photon per second.
Right.
But you still get the interference pattern.
Yeah.
Right, but what he's saying, he's saying if you know exactly which of the two slits the photon goes through, you don't get the interference pattern, you just get 2 lines.
That's correct.
Okay. And I just wanted to make sure because I think I heard that.
That's what's weird about it.
Yeah, that sounds really interesting.
It's because there's really a quantum field. Even though if you were to
right, and the photon
field is
is
established, you
localization of the field, right?
measure it as 1 photon per second, but the field actually extends all the way through.
Oh, okay. I see what he's saying. Okay, now it makes sense. He's saying, imagine you're following 1 photon as it goes through. Okay. Now, yeah. So if you follow that 1 photon, you know where the photon is every single moment. Okay, and this gets into the uncertainty principle too, because if you know where the photon is every single moment, then if you track it, then because it's a point-blank particle, then of course you know it's going to decode it as a spot. But you already know where it is, yeah. Okay.
So,
and then that gets into the whole question of you're observing photons and the way they function in labs.
that's actually kind of interesting. So basically, it's acting as either a probability, or we know where it is, and it's no longer a probability. It's an immeasurable.
Well, in the Copenhagen interpretation, what they would say is that they'd say if you observe the photon, you're simply continuing to observe it. So the wave function is a little collapse, and so it's in a specific spot, and you're just tracking it. That's what the Copenhagen interpretation would say. But then you're getting into that whole crazy observation thing.
Yeah, and I think that's a big mistake a lot of people make is they think observation means human observation, but obviously we can't see a subatomic particle. It's not possible. I think what is meant by observation is just the interaction with another system, correlation.
Well, yeah, some kind of interaction. That's why I said when you set up a double slit experiment, you're shining light at it. There doesn't have to be a person sitting there watching a pattern form. I mean, you could set up timers and whatnot. You could have like phosphorescent paper or computers or some sensors. You could just set this thing to turn on after you walk out of the room, and you can come back later, and there it is. So.
Now, I think one of maybe you can confirm that this is what I understood, that if you put a sensor behind the slits, that it tells you when a photon arrives, if you have those sensors, the interference disappears, even though it's the same slit, the same everything. But if you determine which slit this photon went and which one this one went, then that interference pattern disappears and you only see slits. You see beams of light.
You'd have to have a detector between the light source,
right,
photon source, and the slit.
Yes,
behind the slit.
No. In front of the slit.
No, but if you do it behind, if you do it in front, then you are altering the photon.
That's exactly the point. That's exactly the point. Your detector behind the slit is the screen where you're.
That's right. It's the screen. But
if you have the detector behind the slit after the photon goes through, and you're, with micrometers or whatever, you're using, you move that let's say your photodiode, or in this case would be a photomultiplier. If you're moving that ever so slightly, you'll notice the interference pattern because the intensity changes. If you have your detector in front, and then you measure what's behind, that whole thing breaks down.
Right.
So that's what was, and we did the experiment. It took forever.
Because you have 1 photon at a time.
We got down to 1 photon at a time, and we spent 3/4 of the time just to arguing whether we actually had 1 photon at a time. But if you detect it before it hits the slit, and then you're doing it behind the slit, you're not seeing that pattern, and that really blew our minds when we saw that, because we saw what basically we were told in class, which was kind of cool. And then every time people would walk by the optical bench, like everything was wrong.
Yeah, the shades of the photo.
We had a horrible optical bench. It wasn't like the stuff we had to work. It was really hard to do this experiment.
This is one of the experiments in quantum physics that I never actually got around to doing. I was so pissed.
I chose it and I regret. Well, I invented new ways of using 4-letter words. I felt like an auto mechanic at a shop fixing a car. It was really tough to do.
Well, yeah, I remember doing the photoelectric effect down to
picoamp range. It's the kind of thing where somebody makes a less speed for 20 minutes or something. So we're talking shop now.
The other thing that will be interesting to have a lecture will be explaining polarization, how the polarized light goes through filters, and we saw the other day at the University of Chicago an experiment where you have the polarization equipment, and you polarize the light horizontally and then you polarize vertically. There is no light going through. But then you put in between a polarizer at any other angle, and then the light goes through. Now, if it didn't go through first, how come it goes through now, right? But that would be good to clarify real well.
Well, there's actually two ways to explain that. One way is weight nature factors. Another way is to look at it in terms of photons and their properties. That is. Wow. Well, I guess that's it. Thanks for coming.
Thank you.
These are the diehards.
Yeah, these are the diehards. As soon as I think we start talking about decoherence and Stephen Hawking, a lot of other people are like, I'm out of here. See ya. Thanks for coming. Thanks for having me.